Hello all, I am your TA Balaji and today we will be discussing the solutions for assignment 12. Before we start off and look at the solutions directly, we will have a brief overview of the concepts for the flip-flop, the latch and time borrowing for each of these, right? So first of all, to determine the TPD in a flip-flop based system, the procedure to be followed is the TPD is this, and the procedure is basically you have your TPD here, you have a T setup time before the next clock starts, and there is an undetermined region called T skew here, and there is TPCQ here. So the idea is if you add up TPCQ, this TPD, this T setup, this one, and your T skew, you should finally end up with TC. And all of this summed together should be less than or equal to TC, right? If it goes above TC, then you're going above the time interval. Now, when you rearrange these terms, what you obtain is basically the expression for TPD. And this is exactly how you will compute TPD for a flip-flop based system. Moving on, for a latch based system, right? So let's say you have latch L1, L2, L3 here, but you look at the timing from D1, where D1 is this and it changes its value here. So there is a finite TPDQ where D1 propagates to D1 gives you Q1, which is TPDQ here, which is TPDQ1. Then there is a finite TPD1 corresponding to the combinational block 1, which is this. Then again there is a TPDQ2 which is corresponding to latch 2, and then again there is another combinational block which is TPD2, which is here. This sum together must be the entire period, right? Now when you write down that as an expression, this is what you get. This should be less than or equal to TC, and that's what you have written down. Now to calculate TPD, so the idea is TPD is nothing but the sum of the two combinational blocks, right? Because had it been a flip-flop based system, both these combinational blocks would have just been a single block, and they would have been combinational block, one flip-flop in the beginning, one flip-flop in the end. But here we have divided the combination into two blocks and placed it one here and one here, and that's why we say TPD is TPD1 plus TPD2. This is less than or equal to TC minus 2 times TPDQ, which is basically the delay of this guy and this guy, right? That's how you obtain the constraints for TPD in a latch based system. Now how do you obtain time borrow, that is maximum time borrowed in a latch based system, right? So let's look at this example where you have latch 1 here, latch 2 here, and a combinational block here. Now how much time can this combinational block borrow from the next clock cycle, that is from phi 2? Let's say phi 1 is here and phi 2 is here. First of all, why can you even borrow time? The reason is this is a latch which is dependent on a level. So until you reach this point where it is going to go to 0, until this point you have essentially the output of the combinational block need not be ready until this point, right? Because let's say it changes over here, it still will be reflected on latch 2. Let's say it changed here, it still would be reflected. It changed here, it still would be reflected. So this is the ultimate knee point where it has to be ready by that time. So that's why we say the time borrow is nothing but, let's say if the whole thing is TC and this is TC by 2, right? And we call this as borrowed time, which is borrowed into the next cycle, but it should be ready within setup, right? You need some amount of setup time for even the latch. So hence the time borrow is less than or equal to TC minus T setup plus T non-overlap. Again, T non-overlap is this, where you've said this is TC by 2, this is time borrow, this is T setup, and this is T non-overlap, right? Now when you factor in the skew, obviously you will have to add the skew term here. Hence finally these are the expressions for max min constraints as well as the time borrowing constraints. Note that the flip-flop cannot borrow time because it has to be ready. It's not a level triggered device, rather an edge triggered device, so it cannot borrow time from the next phase, right? And also you can it is said that the two-phase latch system is skew tolerant. The reason being, again, you can allow certain amount of time borrowing. So even if some clock skew happens, the assumption that we make is the clock skew is not so high that it will be more than the time borrow requirement that we put up, right? So that is the reason why we say two-phase latches are skew tolerant. With all this background, let's look at how we can solve the questions for assignment 12. So I'll just give you a minute to look at the table here, the concept of time borrowing here. There are constraints for latches, the constraints for the latch again, and finally the flip-flop constraints, right? So now let's jump into the assignment and look at the questions. Question number 1. For sequencing using flip-flops, determine the maximum logic propagation delay available with a 350 picoseconds clock cycle. Assume there is no clock skew, no time borrowing, right? So for this question, you can look at the solution here. TPD max is T clock minus TPCQ plus T setup. So this is very straightforward from what we have discussed, and we will obtain 265 picoseconds. Second question. Sequencing using flip-flops, determine the maximum logic propagation delay available within a 350 picoseconds. Now you have an additional clock skew term, right? So it just says you need to add an extra term called clock skew and recompute the value. So it was 265 last time, and you subtract and you subtract 45, which is 220 picoseconds, right? Exactly. So that is question number 2. Question 3. For sequencing using latches, determine the maximum logic propagation delay with 350 picoseconds. Assume there is no clock skew and no time borrowing. So again, this is a latch question, and as discussed earlier, the TPD max for the latch question is this, and T minus TPD Q1 plus TPD Q2. So you go ahead and calculate this, and you will obtain 280 picoseconds. Question 4 again asks, if there is a clock skew, will it change? No, it does not change, because we assume that latches are skew tolerant, right? So 280 picoseconds is the right answer. Question number 5. For each cycle, the maximum time the first cycle can borrow into the second cycle, right? So for a flip-flop, as discussed here, right, you cannot borrow time for a flip-flop. That's because it is edge triggered. Hence, the answer for a flip-flop will always be 0. Each half cycle of a two-phase transparent latch with 50% duty cycle. So that is again a two-phase latch. You know what is the time borrow, T borrow, right, which is basically this. Go back and you can plug it in over here, and you will obtain 155 picoseconds. Again, each half cycle with 40 picoseconds of non-overlap, right? If you have a non-overlap time, you will add that in and factor that in, and you will obtain 115 picoseconds. Question A. Question 8 again. If you look at question 8, it asks for the T borrow for a flip-flop, which is again 0, and a two-phase transparent latch, which is 135 given One second. Yeah, so here you've just been given clock skew as an additional term, which was not there in your previous question. There is no clock skew. So if you add clock skew in, which is subtract 20 from the previous answers, you should get 115 as the answer for, 135, sorry, as the answer for question number 9. Question 10. Each half cycle for a two-phase transparent latch with 60 picoseconds of non-overlap, right? Again, if you factor in 60 picoseconds over there, you will subtract out 60 from here, you will get 75 picoseconds, right? That's how you calculate question 10. Question 11. For the sequencing paths shown in figure 2, determine the minimum clock period at which the circuit will operate correctly for each logic design in questions 11 to 12, right? So how do you construct or solve such problems, right? So basically, if you look at this problem, there is a flip-flop here, but all of these are latches. Okay, so if you look at a latch based system where you have a feedback from here as well as here, how do you write down the constraints for what you must choose as the max or the minimum clock period, right? So if you look at the circuit there, you had two loops. So basically you need to make sure that both of those loops are not violated when you choose a particular T clock, right? So that's why we say max, and we look at what could be the first loop's T clock if that were the max, and the second loop's T clock if that were the max. So the first loop has delta 1, delta 2, that's why we say delta 1 plus delta 2 is the time. The second loop is delta 1 plus delta 2 plus delta 3 plus delta 4 by 2. Why? Because this is what we declare as the T clock, right? Yeah. So that's question number 11. You will obtain 360. And again, question 12 asks you for you've been given with different values and you obtain 380 as your answer. So you can go back and calculate the same way. You will obtain 380 as your answer. Okay. Question number 13. So in this question, if you see, the only loop that is there is from this end, right? But however, you need to make sure that the timing constraints are met for this combinational block and this combinational block with respect to the flip-flop, because this, you see here, this is a flip-flop, and again this is a flip-flop, and again this is a flip-flop, right? So you have a flip-flop based system where you cannot violate any timing or have any borrow. Hence you need to make sure that the timing constraints for the individual blocks are met. So you must take the max for the two. So for question number 13, you've taken delta 1 plus delta 2 and delta 3 plus delta 4, and you've taken the max 450. Hence you will make sure that it does not violate for any of the cases, for this or that. Again, for question 14, you do the same. Now you add in the T skew, right? Since it is not skew tolerant now, you need to add in the T skew, and you will calculate that it is 495, right? Yeah. So if you guys have any questions regarding the answers or the solution, please get back to me on the discussion forum. Thank you very much.